So in probabilistic models, we normally assume that our data comes from some probability distribution, but we don't know the parameters describing that distribution. So how do we set them? This video describes maximum likelihood estimation, which is probably one of the most common and most fundamental ways in which we can estimate the unknown parameters of probability distributions. We will look at the general principles underlying maximum likelihood estimation, and we will specifically apply that to the Gaussian distribution. But it can be applied to basically any distribution and many different probabilistic machine learning models, and we will see some examples of that in future videos. If you've watched some of my earlier videos, such as the ones about linear regression, you would have not really seen anything about probabilities or anything with a p in it. So why do we need to estimate the parameters of probability distributions in order to do machine learning? Before explaining how we estimate the parameters through maximum likelihood estimation, I guess it's important to answer this question of why we want to do this in the first place. So in many applications, not just in machine learning, it is useful to deal with uncertainty. And probability theory gives a principled way to do this. For regression, it was relatively easy to come up with a loss function that made sense. But we're now going to look at other tasks, and often it actually becomes a little bit complicated to define or choose a loss function, and a probabilistic perspective can help us to do that. In more complicated models, we might also want to combine different components, and a probabilistic angle on that can help us to figure out how to combine different loss functions. If we are going to incorporate some probabilistic idea into a model, a machine learning model, we need a way to estimate the parameters of that probabilistic model. And maximum likelihood estimation is probably the most fundamental method to do this. And many of the more advanced approaches actually build on maximum likelihood. In this video, we're in particular going to look at maximum likelihood estimation for the parameters of a Gaussian distribution. The Gaussian distribution is probably the most common distribution that you will work with in statistics and probability theory. And this slide shows the univariate Gaussian. In other words, it's a distribution over a scalar parameter x. Towards the end of this video and also in the next videos, we're going to look at multivariate Gaussian distributions where this is actually a vector. So the univariate Gaussian distribution is defined by a mean parameter mu, specifying the center of this bump, and then a width parameter sigma squared, which is the variance. And that captures the spread around this mean. So it basically tells you how flat the distribution is or how sharp the distribution is. Sigma just on its own, that's called the standard deviation. So sigma squared is the variance and just sigma is the standard deviation. So like any probability density function, this thing will integrate to 1. And as in any PDF, you can integrate over a portion of the function to figure out the probability of being in that area. Let's say we're given some data, just some samples. And maybe it looks like this. We've got some data points here, maybe a point here, maybe a point here. Let's add a few points there and there. And what we do is we assume that this data comes from a univariate Gaussian distribution, but we don't know the mean and the variance of this Gaussian distribution. How will we know what the optimal mean and the optimal variance is given this data set? Could you figure out a kind of generic way, maybe with some type of loss function in quotes, to figure out the optimal estimates for the parameters of a probability density function? And for the Gaussian distribution in particular, we can maybe ask, okay, if we've got this generic way, spoiler alert, it's the maximum likelihood estimation method. If you've got this way, how does that actually compare with the sample mean and the sample variance that you might have seen in your statistics or probability theory class? So if I gave you some data like these points that we have here, and I ask you, tell me what the mean of this distribution is. What do you think this mean is? Then the obvious thing that you would do is you would sum up all the values of the different data points. And then you would just divide that by the number of data points, right? That's the sample mean. So if we are going to devise some generic way in which we figure out the parameters of a density function given some data, for the Gaussian distribution in particular, how will that optimal setting for the mean value, how will that compare to the sample mean? And if you've got a good memory, you'll also remember that there's a sample variance equation from your statistics class. How does that compare? Okay, so we're going to use maximum likelihood estimation to do this. The first assumption we make is that just formally that these data points all comes from a Gaussian distribution with some unknown mean and some unknown variance, and that these points are independent and identically distributed. So each of the points are sampled on its own without considering any of the other points, and they all come from the same distribution. So we're given this set of samples, and each sample is a draw from this Gaussian distribution. And as a reminder, we don't know the values of the mu and the sigma squared. So the joint probability density function over these n points that I'm given can be written out in this way if the points are IID. Okay, so you just basically take the value of the PDF under the first point, multiply that with the second point up to the capital N point. This should be a capital N. And that can be written out in a kind of condensed form using this product notation. Now we don't actually know the values of mu and sigma squared. But let's say we guessed some values for mu and sigma squared. And for this data set, the points that we got, we calculate the value of the PDF, given that setting of mu and sigma squared. So some settings of mu and sigma squared, if we plug it in here with the data that we observed, will give high values. Others will give low values. So the basic idea is that we're going to choose our estimates for mu and sigma squared to maximize this number given our data set. So this thing here, we can think of that as something that's a function not of our data, but of the parameters mu and sigma squared. And if we do that, so we're given a data set, given some setting for mu and sigma squared, we can calculate this product, get an answer. If we think about this thingy here in that way, it actually has a specific name. That's called the likelihood of the parameters. And the idea of maximizing this product of values, that's a function of the parameters, that's called maximum likelihood estimation. So this terminology here, thinking of this product of the PDF values for a particular setting of the parameters, that's general. So here we're particularly looking at a Gaussian distribution, but for any distribution, if you basically calculate this product, then that's called the likelihood of the parameters. And if you maximize this function, treating it as a function of the parameters, then that's called maximum likelihood estimation. So let's actually estimate the parameters for a Gaussian distribution using maximum likelihood estimation. It turns out that for many distributions, including the Gaussian distribution, it's actually easier to maximize the log of the likelihood instead of just maximizing the likelihood on its own. Since the log operation is monotonic, the maximum of a function is the same as the maximum of the log of that function. You can think about that for a second, but just convince yourself that you're sure what that means. So one intuitive way in which you can see that the log makes our life easier is that here we've got the product of a bunch of stuff. And at some point we're going to take the derivative of something with respect to the parameters. Now taking the derivative of a product of things, that makes life really painful. So if we're going to take the log here, then from grade 1 mathematics, you can remember that if you take the log of a product, that turns that into the sum of logs. And we will see that in a second. So we like minimizing stuff because then it starts to look like a loss. So instead of maximizing the log likelihood, let's minimize the negative log likelihood. And now we can really call it a loss. So we use the notation that we've used up to now where we call this j, and it's a function of the two parameters. And that's the thing that we're going to try and minimize. To find the estimates of mu and sigma squared, we will set the partial derivatives of the loss with respect to these parameters, we will set that equal to 0, and then we will solve them at the same time, and in that way find the minimum of this loss function with respect to the two parameters. By now, you should be quite familiar with this idea of defining a loss function and then taking the partial derivative, setting that to 0, and using that to find the minimum of the loss, and using that to set the optimal values of the unknown parameters. I will go through these steps relatively quickly, but I encourage you to pause and make sure that you follow the mathematics as we go through this process. So the first thing we do is we start by writing out the loss function a little bit more. So we substitute in the definition of the univariate Gaussian distribution, and then we take the log, which gives us these two terms. And this log we can then split up into two more terms. So we've got a log 2 pi and a log sigma squared. And we're, of course, summing over those two terms. So that results in this term here and this term here. And then we've got the summation over the last term here, which we still have here. Now we're going to take the partial derivative of this with respect to mu, the mean. So we're taking the partial derivative of this whole thing with respect to mu. Neither of these terms contain any mu's in them, so we can just drop them. The partial derivative is equal to 0. This term, of course, has a mu there, so we put it there. We can take the partial derivative inside of the summation, so we get this result here. We take the partial derivative of that. That's grade 2 mathematics, I think, and we're left with this equation for the partial derivative of the loss with respect to the mean. You can go through similar steps to find the partial derivative of the loss with respect to sigma squared, and then you get this result here. And now we're going to set these equations equal to 0. So we're going to set this thing equal to 0, we're going to set this thing equal to 0, and then we're going to solve it jointly. And if you do that, I encourage you to write this out carefully, then you get the following result. So if you set the partial derivative of the loss with respect to mu equal to 0, then you end up with this result. So that's setting this equation equal to 0. And then if you substitute this into this equation here and set that equal to 0, then you get the optimal setting for sigma squared for our variance, and you get this equation here. These equations are quite important, so I'm just going to box them. Now, before coming back to these equations and briefly talking about what they look like intuitively and what whether they make sense, I just quickly want to dig into this likelihood function a little bit more and what it looks like to maximize the log likelihood, or equivalently to minimize the negative log likelihood. So as I said before, we can think of the likelihood or the log likelihood as a function of the parameters of some density. For the univariate Gaussian case, that's the mu and the sigma squared. Now this joint density here that we get out with this product, if we assume that the points are IID, that answer, the values we get from this thing, will differ both based on the data and based on the settings for this distribution. If we're thinking about the likelihood, then you can think of the data set as fixed. And in that case, then this number that you're getting here, this thing here, if the data set is fixed, then this product is just a function of mu and sigma squared. And equivalently, if you think about minimizing the negative log likelihood, because we like minimizing stuff, then this thing here, the negative log of the likelihood, then that's just a function of mu and sigma squared. And that's why we can write the loss as a function of mu and sigma squared. So if we're given a data set of points, right, with these, let's say these points, and let's say we guess some values for mu and sigma squared. So what I'll do is, for that guess, I'm just going to draw out the PDF on top of the x's here. So let's say that's the PDF we get from our particular guess of mu and sigma squared. Then the value of the likelihood, the value of this thing, will be the product of this number here, going up here, multiplying it with that number, that number, that number, that number, and that number. And we're multiplying all of those together. That gives us, for this guess of mu and sigma squared, that gives us the likelihood. And we can calculate the negative log likelihood by taking the log of that number and taking the negative. Now let's say we've got some other guess for our sigma and our sigma squared. And that guess, let's say it looks something like this. And for this guess of mu and sigma squared, we're going to multiply a number here with a number here, multiply all of those together, that gives us the likelihood for this guess. So let's take a third one. We guess a mu and a sigma squared, and it looks like this. And now what we do is we're going to multiply this point here. So we take that, we go up here, multiply that point, 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 go up here, multiply that point. We multiply all of those values together, and that gives us the likelihood. And now the idea is that if you've got a good fit for mu and sigma squared, then this product of the points, the likelihood should be high. It's pretty sure that this green one and this gray one will have a higher likelihood than this red one, which just has a product of a bunch of small numbers here. And equivalently, this red line here will have a large negative log likelihood. The green one and the gray one, they will have smaller negative log likelihoods. And what we did on the previous slide is basically derive equations which tells us how to pick the best mu and the best sigma squared to get the highest possible likelihood or the lowest possible negative log likelihood given a particular data set. And this is the result we then got. For the mean, we just basically take the points, we sum them up, and we divide by the total number of points. And for the variance, we take each point, subtract the sample mean, square that, add that up, and then divide by the number of points. So this equation here actually matches the sample mean from earlier in the video exactly. So if you can remember from your statistics class, you will remember that normally for the sample variance, we have a -1, where now we just have a 1 over n. And this sample variance with the -1 in it, that is an unbiased estimate of the variance. This, the maximum likelihood estimation with just the 1 over n, that does give you basically the estimate that maximizes the likelihood, but it is a biased estimate of the variance. In practice, however, n is typically large enough that it doesn't matter which one we use. When n is small, of course, then it can have quite a big effect. So in Python, you can calculate the standard deviation, the sample standard deviation, with just one line of code. You call numpy.std, and that gives you the standard deviation, just sigma, not sigma squared. And what I want you to go and look up is which one of the two possible equations does Python use. Does it do this version, or does it do the version with the -1 here? And maybe more concretely, which argument should you pass into this function in order to switch between those two versions? Finally, let's look at the multivariate Gaussian. So a multivariate Gaussian distribution is a distribution over a feature vector, something that's multidimensional, not just a scalar as in the univariate case. And again, from your statistics class, you should be able to remember, I sometimes forget, so I need to look it up on Wikipedia, but you should remember that this is the equation for the multivariate Gaussian, where in this case, your features are d-dimensional. So x is an element of, each one is a capital D dimensional vector. That's where that D comes from. And for the two-dimensional case, we can visualize it. So we've got an x1 and an x2. And in this space, then the probability density function is this kind of three-dimensional bump in this space. It can be shown in a very similar way to the univariate case, that the maximum likelihood estimates of the mean vector mu and the covariance matrix sigma are given by these equations. So the optimal estimate for the mu vector is just, again, the sample mean, and the optimal estimate for our sigma matrix, the covariance matrix, is given by this equation here. So we've got each of the data points, and we subtract the sample mean, and we take that and we multiply it with that thing by transpose. That looks a little bit like a squared value, which is similar to what we had for the univariate case. And as in the univariate case, you can either do 1 over n, which is strictly the maximum likelihood estimate, or you can do the sample variance, which is 1 over n minus 1. To get to these results, to get these maximum likelihood estimates, if you go through the same process that we went through before, but now use this multivariate probability density function, you will have to use the matrix and vector derivatives that we looked at in a previous video. As I said at the start of the video, the idea of maximum likelihood estimation is really powerful. It's a workhorse in a lot of the machine learning models that we will look at in subsequent videos.